Hello and welcome to another Learn All Analysis tutorial video. This time the subject is particles. This 3-in-1 video will cover ISO codes, NAS classes, insolubles, total contamination, microscopic ferrographic analysis and visible particles. When we talk about particles in a sample, this is quite a broad topic and we talk about anything from the very small, microscopic and invisible to the naked eye up to particles perhaps centimetres in size that you can pick up with your hands. There are various ways to measure particles in a sample and we're going to cover quite a few of them in this video. I'm going to be using terms like microns or micrometers in this video. So to start off, let's put some of these measurements in perspective. Let's start off with a standard 30cm ruler you've likely used at some point. Most of you will be familiar with a centimetre as a 1/100th of a metre. Millimetres are a 1,000th of a metre and a 1/10th of a centimetre. The next stage smaller is called a micrometre or a micron and is expressed as the Greek letter mu and an m. 1 micrometre is 1/1,000,000th of a metre and a 1,000th of a millimetre. Considering a pinhead is about 2 millimetres, then this means you can stack about 2,000 1-micron size particles side by side across the head. This scale is a bit too small to show on this ruler, so let us take the width of a typical pinhead of 2 millimeters, coloured red, and zoom in on that. We now have a diagram we want to show you on this 2 millimeter scale, or 2,000 micron scale, but that's still too small, so let's make that fit to the screen by zooming in a little further. Now this may seem too small to comprehend now, so let's put some other objects you may be familiar with into play. The width of a human hair is about 80 microns in size, that's 80 microns in size. On the left you can see a green circle and width that is 25 microns, or about 1/3 of the width of a human hair. That is still too small, so I've blown up that green circle onto the right hand side as you can see. Now we're at the stage we want to talk about. On the screen you can see 4, 6 and 14 micron size particles. These will be important when we talk about ISO cleanliness codes later. Just to show the size we're working at, I've put in a human red blood cell into the picture just so you have a sense of how small we actually are. Now that red blood cell is about 6 microns. When we talk about elemental analysis, this for nearly all labs is the largest particle that will be detectable. Now for those of you who think I meant smallest, I didn't. And I want to just make sure you understand that. I meant largest. It may seem strange to talk about a particle being too big to see rather than too small, but when it comes to elemental analysis, this is true. The principal reason for this is that traditional methods work on vaporizing particles, and if they are too big, they are not completely vaporized and are underrepresented. This may come as a shock to you, but this means for most of you, the results you get on your fluid analysis reports are not the true answer as to how much wear particles, for instance, are in the sample. If I was now to tell you that the normal wear is considered anything less than 15 microns, i.e. this 14 micron particle and smaller, and abnormal wear is greater than 15 microns, this means that 2/3 of the normal wear and all of the abnormal wear is underrepresented with traditional elemental analysis. You may be at this point wondering what is the point of all analysis altogether if it misses these larger particles. Well, firstly, something is better than nothing, so if your lab is using these traditional methods, you still get some useful data out of it. But there is an answer for those of you who want the true elemental analysis value too, and that is through a technique called Lube wear. Lube wear is based on acid digestion to break large particles into smaller detectable particles. Acid digestion is an established technique for over 60 years. Lube wear, invented in 2018, is unique in that it can offer digestion routinely and rapidly combined with traditional elemental analysis data to not only give the concentration of particles, but the size distribution too. This is a test developed by and exclusive to oil analysis laboratories in the UK, and a routine test on lube oil samples, meaning you don't have to accept the inferior traditional technologies. If you want to find out more, you can see some of the articles I've written called Is Your Lab's Methodology Failing to Catch Failures on learnallanalysis.com, You can also watch the Lubeware explainer video on this YouTube channel, or visit lubeware.com to find out more. As you can see, I digress slightly there, so just to put into perspective what we are looking at, let's put a grain of very fine sand on the screen at about 70 microns. However, we now are too zoomed in, so let's zoom out again and move this page out the way. That's better. If we zoom out a bit further, we can now see how small we've actually been working at. So moving on, actually, I almost forgot. I need to give credit for the donation of this grain of sand for the picture to my son from his sandpit before I do. So now let's look at a few ways we can measure particles. We have elemental analysis, which is a fantastic tool for breaking down chemically the particles present in your sample and identifying which elements are there. I've already covered the limitations for most labs in that this human hair to the right of the screen is about 40 times too wide to be measured by traditional analysis. But the exception is this Lubeware technique that can measure both large and small particles, not only giving the breakdown chemically, but useful size information too. I have another video on this YouTube channel specifically on elemental analysis if you want to find out more about elemental analysis. Another popular type of testing is laser particle counting for measuring ISO 4406, NAS or SA 4059 cleanliness codes. Laser particle counting can detect particles between 4 and 70 microns. The downside to this method is it gives no elemental and limited shape information. Equally, the tolerances of particle counters tend to be between 150 and 200 microns, meaning you can't measure anything much larger than a grain of sand. An alternative to this method is gravimetric analysis, which weighs the total number of particles but gives no indication of size other than they are larger than a specific filter pore size.
Microscopic analysis is useful for measuring larger particles.
It doesn't give any elemental data and struggles on the smaller particles, but it is great for visualizing the shapes of particles. Finally, there is measurement by eye. Nothing quantitative can be determined from this type of testing to give you a number, but it is great for giving an overall visual assessment of a sample, and is something you can do before posting a sample as well. So let's move on to how all these tests work. Firstly, laser particle counting. The sample is drawn into a particle counter through which laser light is being passed across the flowing liquid. Anything that obscures the light is counted as a particle, and the different channel sizes allow for measurements of different particle sizes. So as you can see, in 1 ml of sample we have detected 8,271 particles greater than 4 microns, 1,622 particles greater than 6 microns, and 193 particles greater than 14 microns. If I asked you to close your eyes to repeat that back to me, you would probably struggle. The reason for that is there are a lot of numbers to remember, and when comparing counts the numbers are too big to work with easily. That is why the ISO 4406 system was created, which is a logarithmic scale, meaning the values double each time. Just to give you an example, looking at the grey column, which equates to the per 100 ml bottle count, if I have 1 to 2 particles in a single 100 ml bottle, then that is a code of 1. If I have 2 to 4, i.e. double it, I have a code of 2. So if I double again to 4 to 8, I have a code of 3, and so on. Now 100 ml is for most labs, including my own, the whole sample, so we can't use the entire bottle for this one test, so most labs will report the values as per ml, the yellow column instead. So if we use this scale based on the sample we just tested, we can see the code equates to 20, 18, 15. This happens to be the typical cleanliness of a new oil. If the code is increased to 21, 19, 16, this is twice as dirty as the new oil. And if it went to 22, 20, 17, it is 4 times dirtier, i.e. double and double again. Before I move on, some of you with very old machinery may have an ISO code with 2 rather than 3 codes, working on the old 5 and 15 micron code system. In this case, the equivalent in new terminology would be to just look at the last 2 codes of the 3-digit code, so 2018-15 is the same as an old 1815. Many people work in ISO codes with the 4, 6 and 14 micron counts. But for completeness, there is a rival system called SAE 4059, which replaced the old NAS 1638 system, which comes from the aviation industry and works on worst case scenario and a single code or class. The classes all work on a per 100ml, i.e. per bottle, and are split into an A to F subclasses. It uses the same ISO 4406 figures, such as the 4, 6 and 14 counts, but also uses 21, 38 and 70 micron as well. So for this example, I will use the same counts multiplied by 100 from the previous example, and because this is the maximum allowable value, I need to pick the lowest value that is still higher than my count. For instance, 827,100 is too big to fit in class 10, and so falls into class 11. So my codes for A, B and C gave classes of 11, 10 and 9. Although not part of the ISO 4406, let's fill in the other counts for the three sizes too. As you can see, there were no particles detected greater than 70 microns, so the class for F was 000. Usually though, most people just work on the overall SAE 4059 code, which is the worst value across the A to F subclasses. In this case, it's 11, so it just works on the worst case scenario. As you can see, a new oil is practically at the top end of the scale, so this scale only really works for the most ultra clean environments, such as in aviation. So unless you work in this industry, you're probably only ever going to come across ISO 4406 codes. We've covered laser counting, but there's also a technique of measuring the condition by visual patches. This technique takes reference known cleanliness patches and compare them to sample that has been passed for a filter paper. These are popular for field use, and the technology to do this type of testing is handheld and fairly inexpensive. The problem is the test is subjective and not as accurate as the gold standard laser particle counting techniques. Visually inspecting may not be a gold standard, but when it comes to sediment testing, measuring these patches by weight is. And for instance, this is still the main test on many petroleum fuel methods to measure the total contamination and sediment. There are quite a few variations on solvents, patch pore size, and volume depending on sample types and specifications working to, but they all have the same principle in common: weighing a filter paper before and after passing a known weight of sample through it. So let's see that in action. First, we weigh a clean filter paper patch, then pass the sample through it under vacuum. Anything larger than the pore size is caught in the patch. We then weigh it again. Doing a few calculations, we then have a weight in milligrams per kilogram. To put in perspective, here are some sample containers that have varying degrees of debris at the bottom. Note you need to look at the edges as the bottle bottom is slightly domed. Now let's put that particle counting in perspective, and that is, the dirtier your oil, the less time a component will last before wearing out. You can have up to a 7-fold difference in life depending on how clean you can get your oil. For instance, in a hydraulic system using servo valves, cleaning an oil from a fairly new oil of 2018-16 to 16-14-12, an 8-fold improvement in cleanliness gives a 3-fold improvement in component life. So what are some of the common causes of high particle counts? Well, the most common cause is actually bad sampling, meaning the person who took the sample accidentally introduced dirt and contamination into the sample. After that are things like recent oil changes, which for ultra clean equipment, new oil is actually quite dirty by comparison. The next cause, which is most significant, is dirt ingress through seals and breathers. The end result being reduced filter life, blocked or bypasses on filters, and ultimately more wear. We'll be covering more on wear particles in part 2, so now would be a perfect chance to pause the video, grab a coffee and get ready for part 2. Welcome back to part 2 of this 3-part video on particles. This next section is actually my favourite part, and I usually find the most interesting as it is about wear particles. To explain abnormal wear though, we first need to explain normal wear. When you get a new component, the surfaces, although they look smooth, are not perfectly smooth, and at the microscopic level look like a mountain range. These particles during the early life of a machine, called the running in phase, get bent and broken off. The exposed surfaces react with lubricant anti-wear additives to produce a protective layer called the shear mix layer. This layer is the final layer of protection when the oil film is overwhelmed, called boundary lubrication. Material is constantly being removed from this layer and added to as part of normal wear of the machinery, which you will recall from section 1 of this video means the particles are all less than 15 microns. Should this boundary lubrication layer be overwhelmed, leading to significant metal-to-metal contact, then the end result is sliding wear. On screen now you can see a particle of sliding wear, which if you look closely you can see it has almost a grain effect to the particle. These parallel lines, called striations, are caused by two surfaces sliding against one another. Let's have a look at another microscope picture now, this one being of sand particles. This is significant as these particles can cause free body abrasive wear, otherwise known as cutting wear. In the previous sliding wear example, it was two surfaces rubbing together causing the wear. This is called two-body wear. In this case, we now have a third particle, such as sand or dirt, which gets between two moving surfaces to cause wear and is called free body wear. To cause the most damage, an abrasive particle needs to be about the same size as the tolerances of the system. This is because too small and it passes straight through, doing little damage, and too large, it never gets to these areas in the first place. This Goldilocks of abrasive particles is perfectly sized to go through and causes a lot of damage. As you can see, it moves along and gouges out long, thin pieces, a little like if you use a mechanical lathe, plane some wood, or simply peel potatoes, which all give the same effect in that particles that come off in long, thin strips. Microscopically, these particles are thin, usually a 1:10 ratio in terms of size. In this example, there is a smaller cutting wear piece at the top right of the picture, sitting on top of the larger piece. So on from free body and back to two body again, and we enter fatigue wear. Fatigue wear is caused by multiple tiny repeated work hardening hits of a surface. To give you an idea of the loads involved on a typical oil film in a rolling surface such as this, it would be an equivalent of trying to balance 10 cars on your fingernail. At these extremely high pressures, the oil film becomes solid at the point of contact and is what causes the wear as it repeatedly hammers on the surface beneath. This starts as pitting, which creates round metal spalls, a little like how if you keep rolling dough in your hands it becomes perfectly spherical, so are these spalls. These spalls, combined with any dirt ingress, are then hammered into the pit further and form a crack, and eventually a chunk breaks off. Here's an example of a spall, which is very early stages of fatigue wear and looks a little like a ball bearing down the microscope. The fatigue chunks are by textbook definition described as orange peel pieces in terms of shape, but I personally prefer to say they look like little islands from an overhead view. Just to give you a flavour of some of the other things you can see during microscope analysis of a sample, these include fibres such as a hair, material or paper. In this case, these fibres are cloth, likely from a rag used to clean the sample point. Next is a rust flake. Now this is similarly shaped to the cutting wear particles we described earlier. Rust flakes don't necessarily have to be the same shape, but it suggests this rust flake was peeled off based on its shape. As I know some people can be a little squeamish about this next picture, I will give you 3 seconds to close your eyes if you are. 1, 2, 3. As you can see, it's an insect leg, most likely an ant, although I'm sure an entomologist will end up writing in afterwards to tell me exactly what it is. This was found in a block breather on an outdoor storage tank in which an ant nest had decided to colonise. This final one is safe to open your eyes now, by the way. I will leave for you at home to have a go at, so please feel free to pause and have a go yourself. For those of you who are having a go at answering and said fatigue wear, yes, you are correct. This is a large fatigue wear piece that is bent over, suggesting it broke off and started to be rolled again. There is also a small fibre at the bottom left of the picture for bonus points. This piece was so large it was visible with the naked eye at approximately 250 microns in length. The next and final part of this 3-part video will cover particles we can physically see, so feel free to have a quick comfort break before watching the final instalment of this series on particles. Welcome back to the final part of this video. This is a test you can do at home too. Even with the best instruments in the world, I personally never diagnose a sample without looking at the bottle first. I realise many labs don't look at the bottle, but this risks missing an awful lot of information. For those that do give visual ratings, this tends to be given as a junior technician role in a lab when it should actually be one of the most senior roles. This is because anyone can look at a sample bottle, but it takes experience to be able to diagnose on the basis of it. This video won't make you an expert in appearances, but it is designed to give you a flavour of visual assessment of samples and help you spot when something doesn't look right. The lab is only ever as good as the sample that is taken, so if you take a sample poorly, then the information obtained from the analysis report will be poorer as a result. The most common cause of a flagged appearance is poor sampling, so if you haven't checked out my video on how to take a good sample, then please do check it out on this channel. To assess the appearance of a sample, I like to break it down into two parts, either fluid and particles. This is why we take two photographs on our reports, one from the side and one from the underneath, to catch both these aspects. A fluid can be bright or dark, hazy or emulsified, or even contain layers or droplets of other fluids. In terms of particles,
The sample can be clear,
show visible debris or sediment. You can also see things like paint flakes, precipitates, and any metallic particles. For metallic particles, it is quite easy to confuse particles, so don't try to assume because they are all yellow, they are brass or bronze, as the oil being yellow often adds a little yellow hue to the particles. Equally, oxidized metallic particles can look like soot, called colloidal, whilst very bright lights can make an oil surface look very shiny and almost metallic. So metal doesn't always look as you would expect it to, and you can be quite easily caught out on this. Let's do a few examples and then you can have a go. You can pause yourself the video if you want to have a go of these ones as well. So from left to right we have a clear and bright sample, a dark and clear, a hazy or cloudy sample, but still free of particles. A little tip for you here, I personally used a line of the floor of the camera rig to see if I can see through. So for example, in the first picture we can see through, but in the third picture we can't. The fourth sample we can see a few specks of debris, but you may have been fooled into thinking that there is a layer on the sample, but that is in fact just a shadow from the sample label you can see. The final picture has two layers, and it is mostly water and a visible sediment at the bottom. You notice this is called layers rather than free water, even though it is free water in this case. Well, the reason for this is until we test the layer, we don't know it is water. We just know we have a denser fluid that is not miscible, i.e. it doesn't mix with the main fluid. So this contamination could be water, glycol, or other lubricating oils. Hence it is best not to guess it is water from appearance alone. So now for you to have a go. Pause now if you need to. Firstly, this first sample, the fluid is bright, but there is a frost effect at the bottom of the bottle. These are usually paper fibres from a paper towel used to clean around the sampling point, or in this example, the customer is manufacturing paper, so this is actually environmental contamination from around the machinery. This next one is ready for you to have a go now. As you can't see through the bottle, this is hazy borderlining on cloudy. The material at the bottom can actually be seen at the bottom of this left photo too. This is microbial growth. The next one is bright but shows a foreign object which turned out to be a leaf. This is a dark sample which looks like engine oil, but in fact is a gear oil that has turned black from oxidized iron particles in it. You can see on the right hand side the large metallic wear, and this was in fact from a gearbox failure. This next one is a little strange. The particles are actually plastic. This machine is an injection moulding machine that mould plastic, and these little beads are part of the material used to make the final plastic called master batch. You can see these particles better under the microscope too. I would just like to thank you for tuning into this video on all things particles in oil analysis, and hopefully you feel you've learned something from it. If you enjoyed, please feel free to share and subscribe to this video or get in touch with us. You can visit our training sites at learnoilanalysis.com or our laboratory for sending samples at oilanalysislab.com. Our door is always open, so please do get in touch.